Okay, so chances are you guys are thrashing through data cleaning right now. And we went through a couple of algorithms last time. So essentially what you're doing when you get the clean data, you apply algorithms to it. You have the machine learning model. So we got to train it. And what you've got to do, teach the algorithm how to make predictions, classifications, or decisions based on your clean data. So that's the model training, and machine learning models, of course, are the outputs, which, of course, we'll get into the metrics. Okay, now we have supervised. Machine learning algorithms. All this means is you have labels. The data is labeled. This is a time-consuming, can be expensive process, particularly in healthcare. There are a lot of these models, these algorithms we talk about. In this particular case, we'll have regression. That's where you have all numeric features. Got logistic regression. All right, so now I'm down in the categorical category, if you will. Regressions by itself. And you've got decision trees. Random forest. And then we'll have support vector machines. And K nearest neighbors. Okay, so I've got regression here in its own category. I'm still under supervised. I've got categorical. We all know the difference between numeric and categorical variables by now. So logistic, regression, decision trees, random forest, support vector machines, and K nearest neighbors. All right, now, for those of you that have all numeric features, you can do regression here, and you can also do support vector regression and random forest regression. Okay, that's it. Okay, that's what you're going to be limited to. So if you end up and you have a data set that you and I have gone over, and we're going to go with all numeric, you're going to do this one, and then you're going to do support vector for regression, and you're going to do random forest for regression. Okay. Those of you that have categorical variables, you pick it. But you will not be doing regression. Okay. You're going to be somewhere in these 5 for supervised. Now, this is pretty straightforward. We're getting ready to go over these. Obviously, we've already done regression with California housing. We've done logistic regression with telecommunications customer churn. Okay, then you have unsupervised. Only going to do one. K means clustering. That means you have no labels. So what do? You have a bunch of features. You turn it loose, and what do you tell the algorithm? The algorithm goes out and finds patterns. That's all it does, all on its own. Let it run. Okay? That's unsupervised. Then you're going to do a nice, simple neural network. I want you guys to do 3 algorithms. Probably you can use your data sets and play with unsupervised if you'd like. That's fine. Sometimes it's interesting to see how the clusters come up. Neural network, we're going to do feed-forward back propagation. Nice, simple, basic. Back propagation. Okay, we'll feed in the data from input nodes over to output nodes, and then we'll do some calculations and it'll feed it through again. So what you end up here is multiple iterations of the neural network. It's simpler than it looks, but I'm going to walk you through it. And what you're going to look for here is convergence. Okay, and it'll talk to you as it goes along. So you're all going to do neural networks. You're going to do any other three algorithms. Feel free to get a wild hair and do all the algorithms. No problem. By the time you get your data clean, guys, you're just stepping through the algorithms. So regression, very straightforward. You guys had this in high school. You got continuous output variables. You got continuous input variables. And in this particular case, like I told you, for some reason, Python wants to call everything linear regression. You're doing multiple regression. Multiple features, single output, okay? So do not worry about that. And then, of course, you can do random forest support vector. You can do regression trees, too. This is a little bit, yeah, you can do that if you like. And then, of course, your neural networks will handle regression as well. So it's pretty simple. You guys, if you just had the amount of sales on the y-axis, size of advertising budget on the x-axis, I can only show 2 dimensions on the board here. This is scatter plot, and you're looking at it. What do I want to do? Linear regression, I want to fit a line. Obviously, with multiple regression, I want to fit a hyperplane. The reason that we're showing it this way is because I want to be able to show you what overfitting looks like. But obviously, when you get in past 3 dimensions, that's what we're talking about with hyperplane. So I want to fit the line to minimize residuals. You've done this a million times, I'm sure. We all know that stats, 2600, 2650. Hoorah, right? Okay. Well, let's just put it this way. What you're looking for here in this class is algorithmic familiarity. That's part of it. The other side is business familiarity. Okay, I'm going through this early, so I didn't. It's quite possible that I could have done more entry work on machine learning, but I didn't want to push you up against not getting to these to work on your project. So we're doing this early. So y-intercept here, slope of the regression line, and you could fit any number of regression lines here, an infinite number, and just rotate these, 360. But what will happen is when you do the residuals, will get all much larger. So what you're trying to do is you want to minimize all these residuals. Clearly, if you've done the regression line correctly, if you add these residuals in with these, there'll be a sum of 0. So you have to square them. Sum of squared. Don't worry about it. The algorithm will do it for you, just like it did with California housing. We have particular performance metrics for regression models, R squared. Okay, notice how much a variance in the dependent variable, dependent feature, your output variable, can you explain by the independent variables? Okay, mean squared error, that's just a mean squared difference. You want to minimize that. Some people use minimum absolute error. I think we're sticking with just mean squared error and R squared. So that's very straightforward on regression. What you've got to do there is to figure out these values. It'll give you an example, an idea of how accurate your regression line is. I were in California housing, and I had to pick one feature that they left out of that data set. Remember, they had population, they had average income, had number of bedrooms, number of rooms, Then there's location, 5 different categorical locations that we had to encode. What they leave out, which I thought was kind of interesting. We got about a 60% explanation of the median house value. I was real surprised. That's a well-used data set on an example. I was surprised they left out square footage. I mean, it's great if you have 5 bedrooms, but if they're all the size of a postage stamp, you don't have anything. That just kind of surprised me. Now, if you're looking at this and you're trying to predict the median house price, what's your business problem? If you were going to write it up and tell me a story. What are you trying to do with that regression?
Predict the home price.
Yeah, your business problem is I've got a house sitting over here and I need to predict how much I can sell it for, given all those independent variables, all the independent features. Now, what do? You say, okay, that's what I'm trying to solve. That's my business problem. I get the metrics. I say I have these metrics. Then I explain those metrics. Remember, we also had percent contribution of every independent variable, especially the location variables. There you have it. Yours will be a lot more complicated. I want you to think about a data scientist who is working on the data coming in off a credit card company. And she's working very hard to handle fraudulent transactions. So all of us are dealing with nice static database, data sets. We truncated them, we're going to do this for this semester. What's she facing? A large fire hose is changing while she's working on it. The data never stops. Okay, this is it's a new order of magnitude different out there in the real world. Okay, so I like the snapshot thing we're doing here because we can't do it any other way. But just remember what's going on in your organizations and when you get out of here. Oh, I had a couple questions over the weekend. What you've got in here, outreach, they came from outreach students. If you're looking for somebody to hire, I'd look right here. Okay. They're taking the hard road. Otherwise, I'd have 7,000 students in here. Feel free to hit me up with an email. Gentlemen, ladies, I'm your agent. Okay? Is it for sports? 5%? 10? I'll negotiate. Okay, supervised machine learning, like we just talked about. There's logistics, logistic regression, binary classification problems. You can do more. Okay, you can use multiple variables. I don't want y'all to fool with that. It looks like this. You've got the classic S-curve. And in this particular case, we're looking at customer churn. Here's the churn probability, means they're going to leave. Churn 0, they're going to stay. Churn's 1, probability they're going to leave. This is a probability. Every machine learning model that you do is probabilistic. It is not deterministic. Okay, so draw the curve in here. You pick a threshold value. You get to pick it when you run the logistic regression. This is I just used binary here. Average number of hours watching content per month and churn probability. Remember, in that particular data set, we had something like 20 independent variables, 20 features. So you get to pick the threshold. Clearly, if the Y value is below 0.5, you'll predict that they're going to stay. If it's above 0.5, you'll predict that they're going to leave. So you predict here that churn's 1. Here you're going to predict churn 0. Now you say to yourself, well, these dots are not 1 or 0. What you have to do is you've got to figure out the threshold that will handle these predictions, because all you're doing is a probability. You're not, if it were deterministic, every one of these red dots would be 0 or 1. That's just not the case. So that's what you're trying to do with logistic regression. We're going to go back to that when we get through this. So again, probability greater than 5, probability less than 5. This is a hyperparameter that you can choose. Okay. Now notice, suppose that you lower the threshold value to 0.2. Okay, this threshold value, let's move it down to 0.2. All right, now what does that mean? This is the way you get to think through it. You can capture more customers at risk of churning because the way you have it set up, because why am I going to capture more? Because if 0.2 is here, all this above it on this curve, you're going to predict churn. Okay, but what are you going to get? You get more false positives. I'm going to misclassify some customers as likely to churn when they're not. Remember, you're trying to predict churn here, which is a negative outcome. So don't get confused when you're predicting a negative outcome. Fraudulent credit card transaction, negative outcome. Okay? If you increase it up to 8.8, okay, now I've moved the threshold value to 0.8. I've increased the number of customers that you will classify as to stay. Okay, but I'm going to reduce the false positives, but now I might miss some customers who would actually churn, who would actually leave. So that's how you set it. This always changes dependent on your data set and what your dependent variable is. All right, decision tree. Oh, by the way, you're trying to do the same thing here. With all those algorithms, logistic regression, decision trees, random forest, support vectors, and k-nearest neighbors. I'm just trying to split classes. I want to divide them and make predictions. That's all I'm trying to do with all 5 of those. Okay, so you've got a hierarchical structure here. Think Christmas tree. I've got hierarchical mean a series of binary decisions made on the input features to determine the predicted class of an observation. Okay, your root node's the top. That's the entire data set. Branch nodes split the data based on one feature. Remember, it's binary. Then your leaf nodes are the terminal nodes. Now, what do you want down here in the leaf nodes? Boy, you'd love for them to be pure. You'd love them to be just one classification or the other. They're not going to be, but that's okay. All right, so that's what it looks like. When you have decision nodes, that means you've got more decisions to make. When you get to leaf nodes, you stop right here. Now, with a big data set and a lot of features, that tree can get very complex. Okay, you can have a lot of levels, and a lot of width and depth. So what you're going to find is we'll have to truncate that. Notice, leaf nodes are where you're going to be doing your decisions. And this is what you'd like to have is as clean a leaf nodes as you could. It would be great if you've got, by the time you've made, let's see, 1, 2 decisions, 3 decisions, then I've bound 3 levels, 1, 2, 3, and say I have 6,000 instances, it'd be really great to have, I'll have 3,000 here and 3,000 here with 0 on the other side. 3,000 on one hand, 0 on the other. So I want to split the data into subsets until I get to the leaves. It would be great if they were pure. What you're going to find is, again, we're dealing with probabilities. You'll find a certain percentage of instances here will be one category, a certain percentage another, and you'll decide, or the algorithm will decide how significant that is. All right, so what I want to do, each split, now by the way, you don't do this. The decision tree algorithm will go ahead and split on your features by which way do I get the most information gain, which means I want to decrease the entropy, which means I want to make pure, I want to get more and more pure subsets. So entropy, that's a level of unpredictability in a data set. It shows how mixed the classes are. So if I'm decreasing entropy, the classes are less and less mixed. Okay, they're more and more pure. See where we're going with this? It'll walk you down through it. So there are hyperparameters here that will come when we get to the notebook, but The algorithm's doing the work. You get to do the translation. All right, now developers will split the data based on Gini index or the information gain that we talked about. Okay. I have a purely homogeneous leaf node. It's pure. I have, where's entropy? Entropy is 0. Pure leaf node means entropy is 0 because I've split the classes exactly. Okay. All right. The objective is entropy 0, pure leaf nodes, and this is great. If your decision tree is too complex, that means your computer can grind. Now, it won't on the size data sets we have, but then you end up with, you get poor performance on new data. More about that as we come to it. You can prune the tree. You can set how many levels. Okay, you can stop it at any time. And also, you can have a certain number of, a minimum number of samples or instances required to create a split. Again, these are parameters you can adjust. Okay, they're simple. They handle categorical and numeric data. This is great, like a regression tree or a decision tree. Decision tree is categorical, regression tree for numeric, and they handle outliers and missing values pretty well. Before you get into this, I would make sure I get rid of all the missing values. But if you had to have one, an algorithm that would handle it, decision trees will do it. Boy, will they grind. Okay, they will require some computation if you get large data sets. Some of you have 500,000–600,000 rows, and a couple of you have 200 features. I guess I'd just go downstairs and have dinner if I were you, and then come back and watch that thing, hopefully get the results. So you're going to have to prune the tree on that one. Yes, they'll overfit, particularly when you let it just run wild. You can get some interesting high variance here when little changes, small changes in training data will result in some interesting, rather startling outputs. So that's what we're talking about there. They're sensitive to the training data. Remember, we're splitting data, training and test. So if it doesn't generalize well, that means you're going to have training data memorized, lousy performance on test data. That's an example data set, customer age, income, shopping frequency, likelihood of buying. This clearly is your output variable. Notice you've got likely, unlikely, and maybe likely. So rather than binary here, we got 3 values that we could possibly predict, probability. And let's just say you turn this thing loose on an algorithm. It decides to split first on shopping frequency, okay, high, low, or medium. So it splits, and it comes up with these 3 decision nodes. So here's high, there's low, there's medium. Notice this is your entire data set, A, B, C, D, E, in the root node, all the instances. A and C go likely to buy, B and D, low, and maybe for medium. This is all you're left with. That's pure, so you stop. Was it split on next? It decides, the algorithm decides to split on income. Less than or equal to 70,000, greater than 70,000. So I've got a binary split here. So what do I end up with? 2 babies and an unlikely. Okay, but I also have both likely to buy here. So I've got my 3 values. A and C likely, E is maybe, and so is B. So that takes care of B and E, and then D is unlikely. Just a nice simple tree. When you get to the bottom, what you'll have down here is you'll either have a pure node, rarely, or you'll hopefully have one with a much larger section of maybe and very few likely or unlikely. Okay, now, if I had to choose algorithms, and I were working this problem for this class, I'd probably skip decision trees and do random forests. And the reason is random forests use multiple decision trees. Why do both? Okay, it'd be better to go ahead and do random forest and support vectors and k-nearest neighbors, but you don't need to do random forest and decision trees. As I said, decision trees do have advantages. Data scientists usually pick that for you. Okay, it's an ensemble algorithm, which means it works off multiple decision trees. The algorithm does the work because it pulls randomly sampled subsets of the training data. And then it turns around and uses randomly sampled subsets of the features. So what it does, eventually it'll work through all the permutations here, and you'll end up with a bunch of decision trees, each one of which makes a prediction. And then you have whichever the number of predictions, when you're doing random forest classification, then you're going to have the mode, how many predictions are of one particular type. Whatever which one occurs the most, that's what you pick. So multiple decision trees. All right. So here's the original data set. I've got 3, 4, 5, 6 customers. This is your age, income, visits, meaning number of visits to the store. Next 3 is your day since your last visit, your product interest, and the classic Y value, did you buy or not? Okay, nice and binary. You're going to run a random forest. You'll set the hyperparameters, it'll do the work. Okay, so we're only going to build 4 new data sets. By the way, your algorithm will run as many data sets as you want it to. All right, I've got to randomly select rows. Notice with replacement, that's very, very important. And you're going to build the new data sets. Your rows can repeat. Every new data set will contain the same number of rows as the original. That process is called bootstrapping. Okay. So here's data set 1. I randomly sampled the instances. So I end up with instance 2 twice, instance 5 twice, and then once on 1 first customer, and then this 4. Notice, same number of rows. The features come along with the rows. So clearly, customer 3, which, 0, 1, 2, you have the same features coming across. Right? Now, because I got this by sampling with replacement. Data set 2, same thing. Notice the different instances that came with this one. There's 3. And there's 4, okay? With replacement, I now have 4 bootstrap data sets. Now, what I've got to do, that's step 1. Step 2, a decision tree for each bootstrap data set. But I only use a random subset of the feature variables or features or columns. Okay, so there's data set 1, bootstrap 1. So what are you going to do? Let's just pick age and income. So I come back up here. There's 1. So I pick age and income. I'm just going to pick 2. You could pick 3. You decide, or your hyperparameters will decide. You set this. So I'm going to end up with these 2 features out of that data set. Come down. So we'll do age and income. Okay, notice, here's your first decision tree. Here's age. All right, what am I going to do? I'm going to split on age less than or equal to 40. All right, now, what does this mean? Yes means I've got age less than 40 over here, less than or equal to. Over here, I've got age greater than 40. Okay, that's the no. Then I'm going to split on income, because remember, I only picked age and income. All right? Income less than or equal to 50, and there's income less than or equal to 80. So I split that. I say, yes, I've got 0 and 1, samples 2, samples 1. What do I have here? Age is less than or equal to 40, and income is less than or equal to 50. At this particular decision, I've only got 3 instances, because remember I only had 6 rows in the 6 samples in the data set. My dependent variable, I had 2 and 1, so 2 go over here with didn't buy, and 1 did buy. There's the same thing going this way. your age is greater than 40, and your income here is less or equal to 80. So I had 1 and 2, didn't buy and did buy. So you're going to run these decision trees. Okay. So I do that. I'm going to pick visits and days for the next one. There you go. And you split there. Then visits and interest. Okay. That's just 3. And then this one I did income and the last visit. Now, I've got the 4 trees. They're randomly generated from instances and from features. Remember, I could have picked 3 features or 4. Now you got to build a forest. All right. So I go back over this hundreds of times. You have to settle on how many times you'll let it iterate. You'll have a lot of trees. All right. So you've got the forest, having run this through all those steps. All right. Now what do? You bring a new customer in. What am I trying to predict here? I've got new customer, age, income, visits, days, since last visit, product interest. Did they buy or not? Okay, with a new customer. Got to run this customer's data through all the decision trees you just created. In our example here, we're only doing 4. Well, there's the first one. That's the decision tree 1 that we created. Remember, we split on age and income. All right, so here's this customer. Okay, all you do is you follow that customer. It comes here, it comes here. Your prediction is did not buy. Okay, this is the original tree. This tree with the new customer is the same as that tree. All I've done is add the new customer in there and then track through the decision tree. Okay, so I use this data again. Decision tree 1, 2, did not buy, 3, did not buy, 4, did not buy. So I've got a nice clean decision. Okay, the new customer's not going to buy. That's your prediction. Could be wrong. All right, now how do you do the random forest? We added up the mode here of what we came up with. In this particular case, all 4 came up, did not buy. It could have been 3 to 1 or 2 to 2. If it's 2 to 2, run some more. Can't make a probability prediction out of a 2-2 split. 3-1, 4-0. Okay. Now, you'll hear the term bootstrapping and then using aggregate results. It's also called bagging. This looks like it's really complicated. It's a lot easier with the algorithm. I want y'all to see how this actually works. It's a very powerful algorithm. Okay, now we allow duplicates, so some entries or samples will not even be included. As a matter of fact, if you have large data sets, which you will have, about 1/3 of the original data in instances won't end up in the bootstraps because of the replacement. That's pretty standard. It's not a mistake. It's just statistics. Okay? Put those entries into an out-of-bag data set. The algorithm does this. Because you didn't use it to create the random forest, you can run the new sample through all the trees in the random forest, add up the votes again. You do the same thing for out-of-bags and the ones that didn't show up, and you can measure accuracy of your random forest because you will get metrics on this. Proportion of out-of-bag samples that the random forest correctly classify. Okay. Pretty straightforward. Okay, incorrect classifications. Here's out-of-bag error. Okay, now, notice I use 2 variables per step, 2 features per step. In our example, you can always go back and use 3 and start doing comparisons. Probably you won't have to do that with the algorithms you're going to run in the class, but your real thing is where do you start with features? It's usually a good idea to start with the square root of the number of features you have. We had 5 features to do the prediction. Square root of 5, close enough to 2. For those of you who have 200 features, all right, you're up around 14. So, okay. Now, support vector machines gets a little bit complex when you look at the pictures. All I'm trying to do is create a boundary that will split the values. And you're going to have values that work back and forth. It could be on one side or the other. that are either mislabeled or it's very difficult. They're highly intermixed. The support vector is only going to come up with this vector. Don't worry about that. I'll show you the picture right here. Okay. Now, this is a nicely split data set, which you will not have, but just suppose that you've got one group here, another group here. And what you've got here is your decision boundary designed to split these two groups so you can make accurate classifications. All right, a soft margin gives you a boundary here where you can account for some values that are getting very close to the decision boundary, and the support vectors themselves will actually define your soft margin. Okay, the algorithm does this for you. What I'm trying to do is get a soft margin here to accommodate errors, because when you come down, you'll get to slack variables. Suppose that you have this. All right, here's decision boundary. It would be great if it were totally clean like I had before, but I added in some more data points. So what do I have here? What I've got here are a couple of data points inside the soft margin, but on the correct side of the decision boundary. Then I get this guy who's outside the soft margin in a long way and outside the decision boundary and on the wrong side of it. So you're going to have to accommodate this guy. You've got to accommodate this guy who's on the wrong side of the decision boundary, and you see the distance. Okay? So I've got to handle that. You could also have green ones up here as well. If you have heavily intermixed data, you'll have all this all over the place, and which is what's going to happen to most of us. And what will happen is this boundary, your algorithm will run that and it'll give you its metrics. So this is the type of thing we're having to deal with when you're doing a support vector. What does this mean to you? You'll get the exact same metrics you're getting off the other ones. It's just a different way to try to split the two groups. And again, if you're heavily intermixed, this boundary will start to get a little wider to accommodate an absolute decision boundary. So in other words, you have to accommodate more errors. Not unusual. You could also take a look at this and say, that guy's an outlier. And now you get to make a decision, do you keep him or not? Hey, nearest neighbors, again, I'm trying to do the same thing. I want a cluster, and I want to take a look at what's going on. All right, so we're going to pick the value of k. You get to pick it. K nearest neighbors. What is the number k that's the single nearest neighbor to the new point, and you're going to classify that as the single nearest neighbor. Okay, I picked k of 11, just out of curiosity. Now, I want to pick the 11 nearest neighbors, their 11 nearest data points, and now I count them up. All right, if I've got 6 in one category, 5 in the other, I go with a 6. Okay? If it's a tie, congratulations. Don't pick even numbers here. Okay, pick 1, 3, 5, 7, and so forth. Now, if you've got low values of k, like a pick k of 1, don't do that. If you do, you better hope your value is right in the middle of the other cluster. Outliers will just blow you up, okay? You're probably going to be overfit too. If you pick it real high, then you're going to get real serious computations here. And, you know, you want something kind of intermediate. All right, so I've got some intermingling here with these three groups. And you figure this is pretty standard. Product price, customer rating. So now you get to figure out how to do k nearest neighbors. Your algorithm will take care of it. You pick k of 1. The new value here comes in at x. You classify it as blue because you use k of 1. Now I'm going to use, what am I, k of 3. Okay, so here's the new value. What do I have? I've got 4 blues, 3 greens, so I pick it blue. Or the algorithm will pick that for you. Then I get this, and what if I pick k of 11, add all this up, Blue are 5, green are 10, red's 2, so you go with green. Yeah.
Why does your K need to be an odd number? Why does K need to be an
I
odd
want to cut
number?
down as many flip of coins. You know, if K is 10 and I had 5 and 5, I'm irritable
Gotcha.
because then I get to flip a coin. All right. These are the metrics. We've already talked about confusing matrix and so forth. This is what we went over: true positives, false positives, true negatives, false negatives, and you'll get to explain all those. This is what the matrix looks like. Actual, actual, predicted, predicted. Remember, we had those 4 numbers: true positives, true negatives, false negatives, false positives. This is the way it goes out. Now, the metrics themselves: accuracy, precision, recall, and F1 score. Notice, accuracy is a blunt instrument. This is a number of correct predictions that you made out of all your predictions. It just groups everything together. It's good to look at it first, okay? Then I go to precision. I've got proportion of true positives out of all the positive predictions made. That's, shall we say, a little more interesting. Recall, true positives out of all the actual positive instances in the data, and then the F1 score does a harmonic mean here that just weights these two together. Probably I'd stick with accuracy and precision. I wouldn't get too deep into metrics. You guys were trying to learn this. But confusion matrix, absolutely. I want you to be able to explain it. All right, unsupervised, K-means clustering. Now, I've got these groups. Got 2 here. Again, I've got a loyalty score, average spend per visit. What do? I've got to figure out a way to define clusters. Why? I don't have labels here. Okay, so all I have is you've got a bunch of, not exactly intermingled, but you'll get intermingling when you get on a real case. And what will happen is I have to pick the centroid. So I'm trying to pick the center of all these points. Now, the simplest way to do that, of course, is to do, just how many variants of X and of Y, and you add them up. Don't worry about that. The algorithm will do that for you, and it'll form centroids. Okay? Now, I want to minimize all the distances of all the blues here and all the reds, so I move the centroid around until that distance gets to be the lowest. Now, you're going to do the difference in the Y's and the difference in the X's and add them up. This is what K-means clustering does for you. It gets to be kind of interesting because you're going to choose your initial number of centroids randomly from data points. You don't know how many clusters you have because you've got no labeling, okay? Assign each data point to the nearest centroid, recalculate them, and you keep going until convergence is reached. So I don't know anything about that data other than I've got 2 variables, average spend and loyalty score. Now, what have I got to do? I've got the algorithm calculates within cluster sum of squares. So what do I try to do? I get a within cluster sum of squares for that centroid and this centroid here for the 2 groups. And then I want to minimize that, which means the centroid is correctly placed. It's called the elbow method. And convergence, when I get the centroids don't change between iterations. This is great. You'll do the elbow method. It comes out like this. I'll show you the code. What you do is you take a look, and wherever this thing stops dropping the most precipitously is the number of clusters. In this particular case, this one dropped very hard at 2, and then it went over to 3. Okay, remember, see, it's starting to ease off. So you would start with 2 clusters. You could use 3 if you wanted to, depending on your data and the way the algorithm's metrics came out. So I look at this, probably 2, but you could go with 3, and it's perfectly fine. It'll actually graph that for you. So we're going to look at this as we go through them. Now, I'm going to put neural networks off to the end until we get through the notebooks here on everything but neural nets. Questions? Now your heads are spinning. All right, who's had analytics before in here? Who's had analytics classes along the way? Higher level. I don't mean stats. I'll have anything. You've done some of this? Okay. Anybody else? Okay, we ran through customer churn the last time, got down here to accuracy and precision. The metrics, remember predicting churn and not churn. There's a confusion matrix. I did not like the way that thing formatted, so I went out to my favorite large language model. I said, let's format that thing differently. Sorry about that. I would love to. I wrote the code. You don't have to do this. So it came up with this, which is great. This is, I ran just a little bit of a different algorithm, but here's what you got. Predicted, actual. No churn, churn, no churn, churn. Here's your true positives, true negatives, true positives. Because we're trying to predict, our positive prediction is churning, and so that's down here with the 1. Okay, so what you do, you take a look, you say, okay, we're going to explain this in just a minute. Now, let's take a look at all the independent variables or the features that you used in the prediction. We used a lot of them. If you remember, we went through the multicollinearity and cleaned that up. And these are your coefficients. You've got gender, and senior citizen, partner, dependence, tenure, and all this kind of stuff. And so it gives you the idea of what your coefficients are. So now I can start looking at statistical significance. So I use this variable, this code, run this model, and again, because I've calculated the coefficients, I get this. Now look, when you get this, you can take a look and you'll see, don't worry about the constant, and don't worry about what's going on here with one-hot encoding. There's your probability greater than z. You guys have all done z-scores, so anything less than 0.05 we'll take a look at. So that is senior citizen. Thank you for my group. Let's see, 2, 3, 4, 5, 6, 7, 8, 9. I've got 10 variables, 10 features that I can use for to just do the statistical significance. Now I'm just going to go ahead and rerun the logistic regression using those. Just out of curiosity, and you're going to get what we're looking at here. Okay. Explanation. Pretty much the same as it was before, and here's how to explain it. Okay. Is it big enough? Can you read that? Sort of. All right, there's accuracy. Correct predictions, both churn and no churn of all predictions made. All right, that's 82%. So out of 1,409 customers, you had 1,150 churn status. Might seem good. These are business implications. Can be misleading for imbalanced data sets like churn. We have a lot more non-churn than we have churns. Precision, 69%. All the customers predicted churn, how many actually did. It's right about 69%. This is where you want to be very careful where you spend your resources. If they're planning retention campaigns, 31% of your efforts are going to you're going to spend them on customers who are not actually going to leave. So you could waste resources here. So clearly, you'd like to increase precision. Recall, of the ones who actually turn, what percentage do we correctly identify? You'd only call it 58% of them, missing the 42% who left anyway. This may be your biggest problem because it misses 42% of the customers who will churn, gives you no chance to retain them. Now, let me tell you about this. When you guys get to this and you say, well, where are you getting these explanation of metrics? If you're not sure, ask GPT. Give the first couple rows of your data set, clean data set, and say, or you can give them the first 5 if you want. Just copy it over and say, here's the data set that I'm running. I ran a logistic regression, and I got this confusion matrix. Be sure and tell the model how you set up your dependent variable. You've got to tell it that I use 0 for no churn and 1 for churn. It's got to know that. Otherwise, it may give you the reverse implications, okay, because you didn't tell it. If it does look, in other words, if you're totally confused what it tells you, go back and see how you encode it. Everybody straight, that's important, having gone there myself. Okay. Now, the F1 score balances precision and recall, and what we've got here, 63%, it is mediocre, and so it's making compromises between precision and recall. This will change depending on what your data set is, but this is how you explain it. By the way, what's our business problem here? Predict churn. That's it. Predict fraudulent credit card transactions. The guy's guilty. He predicted he committed murder. Okay? All right? So we got this, the predicted no churn, predicted churn, actual no churn, actual churn. Business recommendations. Consider adjusting your classification threshold. Always check this because the large language models will really help you here. If you have the least bit of confusion and you want to catch more potential churners, even if it means more false positives. False positive is you predict their churn, they don't. Okay, so come down. You want to check for overfitting, which is always nice. This cell will do that. And you've got some overfitting as far as your accuracy. Training accuracy is 80, and test accuracy is 82. You're pretty good there. Precision drops a bit because of the imbalance in the data set. So that's the logistic regression. Now, what you're going to find is we're going to run this same data set. I did this deliberately on all the other classification algorithms. And you'll see some slight variances here. That's what you'll find when you run the 3 that you're going to run. Okay, now it turns out that data set's pretty clean. So, it's not like losing square footage on California housing. I did put, remember, max iterations here, maximum times you'll let the system iterate here on this hyperparameter. I think the default is 100. If you don't put anything, you just don't have these parentheses here. I usually put a few more than that if I have a lot of features. Okay. Now, if you don't do that and you just leave it, it defaults to 100 and it doesn't converge while it's doing that, okay, don't worry about it. Just go back in there and put in the extra iterations. Okay. It may give you cannot converge, just jack up your iterations. Or you can reduce your features as well. Everybody good on this? Same data set, already clean. All right, same old, brought it in, checked it out, want to make sure everything looked good. The size was what I figured, 7,000 instances, 18 variables. Want to check the columns here just strictly to check. First thing you do, identify independent features. Then we'd identify the dependent feature, which we did. Split the data, still using 80/20. Bring in your decision tree classifier. Make sure you have it up here in your code libraries. All right, run it. This code handles that. Then you make your predictions clearly. That's off your, you've run the fit right here. So what have I done? This is where I'm training the algorithm, the decision tree classifier, my independent training data set, and the dependent training data set, or variable. Okay, I make my predictions, then I look for accuracy, etc. Looking to get. Okay, accuracy 0.73, precision 0.48, etc. If you'll notice, this is lower than a logistic regression. Okay, to get into that would be computer sciencey stuff. Okay. You got a little bit difference on your confusion matrix. Now, when you look at this, it's really neat because I haven't done a thing here with the decision tree. So what did the model do? Okay, it's already done this. So now I say, give me the figure to show me what you were doing up here with training it and then testing it. All right, so what did it do? The model comes in here on its own. All this does is draw a figure. Okay, you've already done the calculations. All the stuff up here is this. Okay, I'm looking at this graphically. This is decision tree. First split, it chose split on what did it choose? Do you have a contract or not? True comes this way, false comes that way. These people have no contracts or some kind of contract. This one they do. Okay, now notice you've got the class here is to not churn because this is your data set here. If you had 41 and 15, you get about 56, 56, I'm sorry. And so you've got this number of variables for contract. Contract in this case, less than or equal to 0.5. In other words, it's a yes, no, 0, 1. So that'll be greater than 0.5. So contract here, no contract there. It picked it on the Gini index. In other words, to the algorithm, and it ran through all those features. It considered each one. It picked this one to give you what? The greatest decrease in entropy. In other words, I want to get the most information gained. So that's what it picked first. If you come this way, where I'm less than 0.5 for contract, so I don't have one, now it shows fiber optics. It chooses this for you. Over here it picks monthly charges. Notice interesting, if you get a more intense color, you get a more homogeneous node. I've got 2,370 here and only 181. So it's not churn. So this is very intensively not churn. Now over here, I don't have a real, it's still not churn, but you notice these two are almost together, 1,700 and 1,300. So I still have a lot of mixture here where I don't have there. All right, then it splits on fiber and it starts working its way through the tree. All right, that is a big, hairy tree. By the way, if you want to alter your figures, you can change these numbers. These are hyperparameters. You can control the first number in fixed size here, controls the horizontal spread, and the 10 is the height, so you can blow it up. By the way, if you do, you'll end up having to scroll back and forth this way on the screen and up and down. So the point I was making on this That's what this is. Once you did this, it produced this tree to itself and then did all these calculations for our metrics. Well, that's nice, but what would be really nice is to go ahead and optimize your hyperparameters. In other words, what you set up here. All right, so I come in, I said, okay, what do I get? Let's go ahead and do maximum depth, okay? Remember I said prune the tree? This is pretty deep here. This may be 15 levels down. So what we're going to pick is how many levels I'll let it grow. If I pick lower levels 3, simpler trees might miss patterns. If you pick higher values such as 7, I get complex trees that might overfit. The more complexity, the more tending to overfitting. Now, the minimum samples you get to pick. If you pick 5, you need at least 5 customers in a group before you can split it into smaller groups. Higher value, simpler trees, obviously. Lower values, more detailed splitting, deeper trees. Minimum samples, minimum number required in a terminal leaf node. Set it to 4. Every final node must have 4. That's great. Lower values, very specific small groups. Higher values, force broader groupings. If I get broader groupings, I've got a shallower tree. If I have very specific small groups, I get a deeper tree. All right, then it'll handle, those are the ones you pick, those 3. Then you'll do grid search, CV, that's a code library. It'll handle all the combinations. So I've picked here 3, 3, and 3, 27 combinations. Okay, now I'm going to optimize hyperparameters. I pick max depth, I pick 357. By the way, the 3 by 3 by 3 here counts for the number of variables I put in here. I put 3, 3, and 3, so that's 27. That works pretty well. Then I run grid search, find the best hyperparameters, and here they are. Depth of the tree I want to limit to 5. Minimum samples per leaf at 4. Samples per split 2. Then I go with best decision tree classifier here because I'm using best hyperparameters. Run it again. All right, now I've decided I want to go with 40-10 because I want to get this thing split. But notice what you have. Can't read it really well, so I come down, I go with 2016 so I can actually read it. And it starts here with, okay, go with contract like we said, then fiber optic monthly charges, pretty much like the big tree we saw up there at the top. You can almost read it at the bottom. Okay, so that is when I've optimized my hyperparameters, so I don't have that big hairy tree, and we'll go over all the variables on Wednesday, okay? That's decision trees.